The Rhine River, March 1945. 400 feet of churning water, the last barrier protecting Germany. Combat engineers are hammering steel pins into wooden panels, racing against time. 3 hours ago, this was just a pile of parts, stacked by the riverbank. Now, Sherman tanks weighing 30 tons are about to drive across what was open water this morning. The German commanders across the river are watching through binoculars, and they can't believe what they're seeing. They blew every bridge across the Rhine thinking it would buy them weeks. The engineers building this bridge never used cranes, never poured concrete, never did anything that traditional bridge building required. They just connected panels like puzzle pieces and pushed the whole thing across the river. By the time the sun sets, an entire armored division will be on the other side, and the war will effectively be over. This isn't about one bridge over one river. This is about the moment warfare changed forever, when a British civil servant who played with model bridges in his basement figured out something the military engineers had been trying to solve for centuries. His name was Donald Bailey, and before he came along, building a bridge that could carry tanks took specialized equipment, trained engineers, and weeks of dangerous work. After Bailey, it took a couple of trucks full of parts and 3 hours. Field Marshal Montgomery, the man who commanded Allied forces in Europe, said the Bailey Bridge was worth its weight in gold. General Eisenhower called it one of the 3 most important pieces of equipment the Allies had, right up there with the landing craft and the Jeep. Without Bailey bridges, D-Day might have failed. Without them, the advance across Europe would have stalled at every blown bridge and destroyed crossing. This is the story of how one simple idea, sketched on the back of an envelope, became the weapon that let the Allies move faster than the Germans could retreat. Rewind to September 1939. Germany invades Poland. World War II has started. The British Expeditionary Force ships across the Channel to France, ready to fight. They bring with them all the equipment a modern army needs: tanks, artillery, trucks, ammunition, fuel, food, medical supplies. And buried in the logistics lists, bridging equipment. Lots of it. Heavy, complicated, specialized bridging equipment that requires trained engineers and heavy machinery to deploy. Fast forward to May 1940. The German blitzkrieg smashes through France. The British Army is falling back toward Dunkirk, abandoning equipment as they go. They leave behind almost everything. Every tank, every truck, every piece of artillery, and all of their bridging equipment. When the evacuation is over, and 300,000 men are safe in Britain, they're safe, but they're empty. The British Army has essentially nothing left except the soldiers themselves. Churchill looks at this disaster and immediately starts thinking about the next phase. Britain needs to rebuild its military from scratch. They need tanks, planes, ships, all the hardware of modern war. But they also need something less glamorous, but just as critical. They need to solve the bridging problem. Because armies move on roads, and roads cross rivers, and rivers without bridges are walls that stop armies dead. The British military has been struggling with field bridging since World War I. The basic problem is this: you need a bridge that's strong enough to carry heavy vehicles, light enough that soldiers can carry the parts without machinery, simple enough that regular troops can assemble it without years of training, and fast enough to deploy under fire before the enemy can stop you. Oh, and it needs to work for any span length, any river width, any terrain. For 20 years, military engineers have been trying to square this circle. They've tried dozens of designs. None of them work well. The standard British military bridge in 1940 is called the Inglis Bridge. It's made of massive steel girders that weigh tons. You need cranes to lift the girders into place, which means you need heavy equipment at the bridge site, which means you need intact roads to get the equipment there, which means if the enemy blows the roads on the way to the river, you're stuck. The Inglis Bridge can span decent distances and carry heavy loads, but it's slow, really slow. Building an Inglis Bridge takes a week or more, and that's if everything goes perfectly, which in combat it never does. There's also the Hamilton Bridge, which is lighter than the Inglis, but weaker and even more complicated to assemble. There are pontoon bridges, which float on the water and can theoretically span any distance. But they're vulnerable to currents, debris, and enemy fire, and they take forever to deploy. Every system has drawbacks. Every system requires specialists. Every system takes too long. And there's another problem that makes everything worse. None of these bridging systems are standardized. The Inglis Bridge uses different parts than the Hamilton Bridge. Units from different divisions can't share equipment because nothing's compatible. If you need to build a bridge longer than your equipment allows, you can't just combine 2 systems. They don't work together. If a component breaks, you need a replacement part made specifically for that system. which means a long wait for manufacturing and shipping. The whole setup is a logistical nightmare that slows down military operations and gets soldiers killed. The War Office knows this is a crisis. In June 1940, right after Dunkirk, they issue an urgent requirement. They need a new bridge design. It needs to meet a long list of seemingly impossible specifications. It has to carry a load of at least 25 tons, enough for medium tanks. It has to be buildable without heavy equipment or cranes. The parts have to be light enough for infantry soldiers to carry by hand. It has to be simple enough that troops can assemble it with minimal training, ideally in a few hours. It has to be modular, so you can scale it for any span length. It has to use materials and manufacturing processes that British factories can produce quickly and cheaply. And they need it now, not in 5 years after extensive research and development. Most military engineers look at these requirements and think it's impossible. You can't have all of those things in one design. Strong, light, simple, fast, modular. Pick 3, maybe, but not all 5. The requirements contradict each other. A bridge strong enough to carry tanks is going to be heavy. A bridge light enough to carry by hand is going to be weak. It's basic physics. You can't cheat the laws of nature. But there's one engineer who thinks differently. His name is Donald Coleman Bailey, and he's not a famous man. He's not a brilliant university professor or a celebrated military officer. He's a civil servant, a mid-level employee at the Royal Engineers Experimental Bridging Establishment in Christchurch, on the south coast of England. His official job is to evaluate bridge designs submitted by other people, test prototypes, write reports. It's bureaucratic work, not exactly the cutting edge of innovation. But Bailey has a hobby. In his spare time, in his home workshop, he builds model bridges. Not toy bridges, but carefully engineered scale models that he uses to test structural concepts. He's obsessed with the problem of making bridges simpler and more efficient. He's been thinking about this for years, long before the war started. Back in 1936, he actually submitted a proposal for a new type of modular bridge to his superiors at the War Office. They looked at it and filed it away. Not interested. The military isn't looking for radical new ideas from junior civil servants. They want proven, conventional solutions. But now it's 1940. Britain is desperate, and the old solutions aren't working. Bailey dusts off his old ideas and starts refining them. He's thinking about the core problem differently than everyone else. Most engineers are trying to build a bridge, a single structure optimized for specific conditions. Bailey is trying to build a system, a set of interchangeable parts that can be configured for any situation. It's like the difference between building one custom car and designing an assembly line that can build any car. The breakthrough comes in late 1940. Bailey is sitting at his desk, probably frustrated with the slow pace of official channels and the resistance to new ideas. He grabs an envelope, the back of a piece of mail, and starts sketching. The drawing is deceptively simple. Instead of one massive load-bearing girder, he draws a truss made of small, identical panels pinned together. Instead of requiring cranes to lift heavy components into place, the panels are small enough that 4 men can carry each one. Instead of building a custom bridge for each crossing, you have a modular system where you can add more panels to make it longer, stack them to make it stronger, or combine them in different configurations for different loads. He shows the sketch to his boss, a man named Major Everall. Everall looks at it for about 10 seconds and realizes he's looking at something important. He takes it immediately to the Ministry of Supply, the government department responsible for wartime production. The officials there are skeptical at first. This drawing on the back of an envelope is supposed to solve a problem that's stumped military engineers for decades, but they're desperate enough to give Bailey a chance. They tell him to build a prototype. He has 3 months. Bailey and his small team work around the clock. They're not just designing the bridge. They're designing every aspect of how it will be manufactured, transported, and assembled. Every component has to be simple enough to make with standard steel fabrication techniques available at any factory. Every connection has to be strong enough to carry battle tanks, but simple enough to assemble with just a hammer and pins. Every measurement has to be precise so that parts made at different factories will be perfectly interchangeable. The panel is the key component. It's a rectangle of welded steel, 10 feet long and 5 feet tall. The interior is a truss pattern. Diagonal braces that provide strength without adding excessive weight. The corners have lugs, male and female connectors that let panels lock together with pins. Each panel weighs about 570 pounds. That sounds heavy, but it's light enough for 4 soldiers to lift and carry. More importantly, it's light enough to load onto a standard military truck. You can stack panels in a truck, drive them to wherever you need a bridge, and unload them by hand. No special equipment required. The genius is in how the panels connect. The lugs at each corner align with the lugs on adjacent panels. You slide a steel pin through the aligned holes and hammer it in. That's it. No welding, no bolts and nuts, no complicated fasteners, just pins and a sledgehammer. This means assembly is fast and doesn't require specialized tools. It also means disassembly is just as fast. Pull the pins out, separate the panels, load them back on the truck, and you can reuse them somewhere else. Bailey's team builds the first prototype in early 1941. They set it up at the testing ground in Christchurch and start putting it through torture tests. They drive tanks over it, back and forth, hundreds of times. They load it with pig iron until it groans under the weight. They simulate damage by removing panels to see if the structure can still carry loads with parts missing. They test it in rain, in wind, at different temperatures. They are trying to break it, looking for weaknesses. The bridge holds. More than that, it exceeds expectations. The modular design means they can configure it for different spans and loads just by adding or removing panels. Need a stronger bridge? Stack 2 layers of panels on top of each other. Need an even stronger bridge? Add more panels to the sides. Need to span a longer distance? Add more sections. The system is endlessly adaptable. The Ministry of Supply is impressed. In July 1941, they approve full production. By December, the first Bailey bridges are in military service. They're about to face their first real test, and nobody knows if they'll actually work under combat conditions. The prototype tests were controlled. Scientific combat is chaos. Exploration development. The Bailey Bridge isn't a single thing. It's a system. Think of it like building blocks, but for bridges. There are main components that all work together. And understanding how they fit is key to understanding why the Bailey was revolutionary. First, the panels. These are the backbone of everything. Each panel is that 10-foot-long, 5-foot-tall rectangle of steel truss. The interior has diagonal bracing in a specific pattern, carefully calculated to distribute loads efficiently. The steel is high strength, but not exotic. It's the same grade of steel used in building construction and shipbuilding, which means British factories can produce it without retooling. The panels have lugs at all 4 corners, little protruding tabs with holes drilled through them. These lugs are precisely positioned so that when you line up 2 panels side by side or end to end, the holes align perfectly. You can then drive a steel pin through the aligned holes, locking the panels together. The pins themselves are simple. They are just solid steel rods, about 1.5 inches in diameter, with a slightly tapered end to make insertion easier. Some versions have a split pin or a locking tab at the end to prevent them from sliding back out. But the basic design is just a rod. You hammer it in with a sledgehammer. That's all. The friction and weight of the structure keep the pins in place once they're seated. Second, there are transoms and stringers. These form the roadbed that vehicles actually drive on. Transoms are horizontal beams that span across the width of the bridge, resting on the bottom chords of the panel trusses. Stringers are longitudinal beams that run the length of the bridge, sitting on top of the transom. Together, they create a grid that supports the roadway surface. The roadway itself is made of wooden planks called chesses, or in later versions, steel plates. The chesses just lay on top of the stringers, held in place by their own weight, and sometimes by cleats or clips. Third, there's the launching nose. This is a crucial component that most people don't think about. When you're building a bridge, you can't just shove one end out into empty air and hope it doesn't tip over. The launching nose is a lightweight extension that attaches to the front of the bridge during construction. It's angled downward slightly and has a roller at the end. As you push the bridge forward from your side of the river, the launching nose extends out over the gap, distributing the weight so the structure doesn't collapse under its own mass. Once the bridge reaches the far bank, you remove the launching nose and finish the assembly. Fourth, you have rollers and other assembly equipment. Rollers are basically big steel cylinders that you place on the launching bank. The bridge sits on these rollers during construction, allowing you to push it forward smoothly. There are also ramps and other positioning equipment, but all of it is simple. No engines, no hydraulics, just mechanical advantage and human muscle. The beauty of the system is its modularity and how it scales. A single panel is rated to carry a certain load. If you need more strength, you add more panels to the sides, creating a double or triple configuration. If you need even more strength, you stack panels vertically, creating a double-story or even triple-story bridge. Each configuration has been tested and has known load ratings, so engineers can calculate exactly what configuration they need for a given situation. For example, a single configuration, meaning 1 panel wide on each side and 1 story tall, can span about 30 feet and carry light vehicles. A double single, 2 panels wide on each side, and 1 story tall, can span 60 feet and carry medium tanks. A triple double, 3 panels wide and 2 stories tall, can span over 100 feet and carry the heaviest tanks and equipment the military has. And here's the really clever part. You can build the entire bridge from one side of the river. You don't need workers on both banks. You don't need to string cables across the gap first. You don't need boats or pontoons. You assemble the bridge on your side, resting on rollers, and you push it across the gap like you're extending a telescope. The launching nose keeps the front end from tipping over as it cantilevers out into empty space. Once it reaches the far bank, you settle it onto prepared supports, remove the nose, add the roadway, and you're done. Let's walk through a real assembly operation to see how this works. It's April 1943, somewhere in North Africa. The British 8th Army is pushing west across Tunisia, chasing Rommel's Afrika Korps. They reach a wadi, a dry riverbed that's been turned into a defensive line by the Germans. The British engineers need to get tanks across. The wadi is 50 feet across and about 15 feet deep, with steep sides. A perfect tank trap. The engineer unit calls for a Bailey bridge. Trucks arrive carrying the components: panels, transoms, stringers, chassis, rollers, pins, and hand tools. No cranes, no powered equipment. The officer in charge does a quick calculation based on the span and the load. They need a double single configuration, 2 panels wide on each side, 1 story tall. That'll carry the Crusader and Sherman tanks they need to get across. The first step is preparing the launch site. Soldiers clear away any obstacles and level the ground. They place steel rollers on the ground parallel to the wadi, spaced according to the manual. These rollers are where the bridge will sit during assembly. On the far side of the wadi, other soldiers prepared the landing site, making sure it's level and solid. They might add wooden cribbing or stone to create a stable foundation for the bridge to rest on. Now the assembly begins. For soldiers pick up the first panel and carry it to the launch site. They set it on the rollers, with the lugs facing the right direction. Another team brings a second panel and positions it next to the first, aligning the lugs. A soldier with a sledgehammer drives pins through the aligned holes, connecting the panels. This forms the first section of one side truss. They repeat the process on the other side, building both trusses in parallel. The 2 trusses are now sitting next to each other on the rollers, but they're not connected yet. Next, they add These are horizontal beams that connect the 2 trusses, turning them into a unified structure. Soldiers lift a transom, position it across the 2 trusses, and clamp it into place. The transoms have end fittings that hook onto the bottom chord of the panel trusses. No pins needed for transoms. They just rest there, held by gravity and friction. They add several transoms along the length of the assembled section, spacing them according to the design. Now the first section is complete. It's a 10-foot-long segment of bridge sitting on rollers. They add the launching nose to the front end. The nose is a lightweight structure, maybe 50 feet long, that pins onto the front of the bridge and angles downward slightly. It has a roller wheel at its very front tip. With the nose attached, they start pushing the bridge forward on the rollers. Dozens of soldiers line up behind the bridge and push. It's hard work, but the rollers make it manageable. The bridge slides forward, the launching nose extending out over the wadi. Once they've pushed the first section about halfway across the rollers, they stop and add the next section. 4 more soldiers bring another pair of panels. They position them behind the first section and pin them together, extending the trusses. They add more Now the bridge is 20 feet long. They push it forward again. The launching nose is now extending further out over the wadi, cantilevering into empty space. They repeat this process, adding sections and pushing, adding sections and pushing. It's like building a bridge that grows longer as you assemble it. The launching nose is crucial here, because without it, the front end of the bridge would just tip over and plunge into the wadi once it extended past the support of the rollers. The nose distributes the weight and keeps the bridge stable as it reaches across the gap. Midscript CTA, around 15 minutes in, drop a comment if you ever crossed a Bailey Bridge. They're still standing all over the world, 70 years after the war ended. After about 2 hours of steady work, the launching nose reaches the far side of the wadi. Soldiers on that side guide it down onto the prepared landing site. The roller wheel touches down, and suddenly the bridge is supported on both ends. The structure settles, taking its full weight on the supports. Soldiers remove the launching nose by pulling the pins that held it to the bridge. The nose is set aside to be reused on the next bridge. Now they finish the roadway. Teams of soldiers carry stringers, the longitudinal beams, and place them on top of the transom. The stringers rest on the transoms and run the full length of the bridge. Then they lay the chassis, the wooden planks, across the stringers. The planks are 10 feet long and about a foot wide, thick enough to support vehicle weight. They lay them side by side until the entire roadway is covered. Some soldiers add railing sections on the sides, steel pipe frames that help guide vehicles and prevent them from driving off the edge. The final step is testing. An engineer walks the length of the bridge, checking every connection, every pin, every component. He's looking for anything that might be loose or misaligned. If everything looks good, he signals to the far side. A tank, usually a light one for the first crossing, drives onto the bridge. The officer watches carefully as the tank proceeds across. The bridge flexes slightly under the weight, which is normal and expected. The tank makes it across without incident. The bridge is now open for traffic. From the moment the trucks arrived, with the components to the moment the first tank crossed, 3 hours had passed. 3 hours to build a bridge across a 50-foot gap in hostile territory. Without cranes or heavy equipment, using nothing but hand tools and muscle. By the end of the day, an entire armored brigade will have crossed that bridge. The Germans on the other side of the Wadi are in full retreat because the British moved faster than they thought possible. This scene plays out hundreds of times during the North African campaign, and then in Italy, and then in France after D-Day. Every time the Germans blow a bridge, every time the terrain forces the Allies to cross a river or gorge, Bailey bridges appear. The German military watches this happen over and over, and they can't figure out how to stop it. They destroy crossings, thinking it'll delay the Allied advance by weeks. The Allies build a Bailey bridge in hours and keep moving. It's a logistics miracle that the Germans have no answer for. But not every crossing is a simple 50-foot span over a dry wadi. Sometimes the challenge is much bigger. Sometimes it's a major river, hundreds of feet across, with fast currents and enemy fire coming from the far bank. That's where the Bailey system really proves its worth, and where the engineers have to combine it with another technology: pontoons. A pontoon bridge is exactly what it sounds like. Instead of resting on supports at each end, the bridge floats on boats or floating platforms. The concept is ancient, going back thousands of years. The Romans used pontoon bridges, so did Napoleon. The basic idea never changes. Line up a bunch of boats, lay a platform across them, and you have a floating bridge. But making it work with heavy military vehicles, in fast rivers, under fire, is a completely different challenge. The British military has been using pontoon bridges since World War I, but they're a pain to work with. Traditional pontoons are either metal boats or inflatable rubber rafts, and each one has to be positioned carefully, anchored against the current, and connected to its neighbors. The roadway is usually wooden planks laid across the pontoons. The whole thing is labor-intensive, takes forever to deploy, and is vulnerable to enemy fire because each pontoon is a separate target. One well-placed artillery shell or bomb can sink a pontoon, and the whole section of bridge collapses. But Bailey bridges change the equation. Engineers realize they can combine Bailey panels with pontoons to create floating bridges that are stronger, faster to deploy, and more resilient than anything that came before. The panels provide a rigid roadway that distributes the load across multiple pontoons. If one pontoon gets damaged, the bridge stays up because the Bailey panels transfer the weight to adjacent pontoons. It's the best of both systems. Here's how it works. Instead of setting the Bailey bridge on fixed supports at each end, you set it on floating pontoons spaced along the river. Each pontoon is basically a steel boat, about 25 feet long and 8 feet wide, with a flat deck on top. The pontoons have anchor points where you can attach cables to hold them in position against the current. You launch the pontoons into the river, position them in a line across the water, and anchor them. Then you build the Bailey bridge on the near shore, just like before. But instead of pushing it across a gap, you push it out onto the pontoons. The pontoons support the weight of the bridge, and the bridge provides a stable roadway. The result is a floating bridge that can span hundreds of feet, maybe even 1,000 feet or more if you have enough pontoons. It can carry the same loads as a fixed Bailey bridge, 30 tons or more, depending on the configuration. And you can build it almost as fast as a fixed bridge, assuming you have enough pontoons and boats to position them. This technique becomes crucial during the advance across Europe in 1944 and 1945. The major rivers, the Seine, the Rhine, the Elbe, are all wide, fast-flowing obstacles that the Germans use as defensive lines. They blow every bridge as they retreat, and the rivers are too wide and too deep for fixed Bailey bridges. Pontoon-supported Bailey bridges become the standard solution. Let's talk about the Rhine crossing, because that's where the Bailey bridge faces its ultimate test. The Rhine is the last major natural barrier protecting Germany. It's a massive river, in some places 400 feet across, with a strong current and steep banks. The Germans know that if the Allies cross the Rhine in force, the war is effectively over. So they defend it with everything they have. They blow every bridge. They mine the banks. They position artillery to cover every likely crossing point. They station troops in fortified positions with orders to fight to the death. The Rhine is supposed to be impenetrable. The Allies know they have to cross, and they plan multiple crossings at different points to spread out the German defenses. One of the major crossings happens at Remagen in March 1945. Through a combination of luck and daring, American troops captured the Ludendorff Bridge, the only bridge the Germans didn't manage to blow up. But the bridge is damaged and won't support heavy traffic for long. Engineers need to get another crossing established fast before the bridge collapses or the Germans counterattack and destroy it. Bailey bridges save the operation, while infantry holds the bridgehead. Engineer units start building pontoon-supported Bailey bridges on either side of the captured bridge. They're working under fire. German artillery is dropping shells into the river, trying to sink the pontoons. Snipers are taking shots at the engineers. The current is strong, making it hard to position the pontoons accurately. But the engineers keep working. They launch pontoons into the Rhine, fighting the current to get them into position. Each pontoon has a crew of 3 or 4 soldiers who paddle or use small outboard motors to maneuver it. Once a pontoon is roughly where it needs to be, they drop anchors upstream and downstream. Heavy weights connected to the pontoon with steel cables. The anchors dig into the riverbed, holding the pontoon steady against the current. They space the pontoons about 30 feet apart, close enough that the Bailey Bridge can span from one to the next without excessive sag. On the near shore, other engineers are assembling the Bailey Bridge. They're using a triple-double configuration, 3 panels wide on each side and 2 stories tall, one of the strongest configurations possible. This bridge can carry anything, even the heaviest tank recovery vehicles. They built it in sections on rollers, pushing each section out onto the pontoons as it's completed. It's slow, dangerous work. Shells are landing in the water, sending up geysers that rock the pontoons. One pontoon takes a direct hit and sinks, forcing the engineers to replace it while under fire. But they keep going. Section by section, the bridge grows longer. After about 6 hours of work, much longer than a normal Bailey Bridge because of the combat conditions and the complexity of positioning pontoons, the bridge reaches the far shore. Engineers on that side secure it to land-based supports. The roadway goes on. The bridge is open. Within hours, tanks are crossing, then trucks, artillery, more troops. An endless stream of men and equipment pouring across the Rhine. The Germans throw everything they have at the bridge. Artillery fire, airstrikes, even frogmen trying to plant explosives on the pontoons. But the Bailey Bridge holds. When pontoons are damaged, engineers replace them without shutting down traffic. When panels are hit, they swap them out. The bridge stays open, and the bridgehead expands. This scene repeats at multiple points along the Rhine. Everywhere the Allies need to cross, Bailey bridges appear. The Germans are shocked by how fast the crossings happen. They expected the Rhine to hold up the Allied advance for weeks, maybe months. Instead, within a week of the first crossing, the Allies have multiple bridges up and running, and entire armies are streaming into Germany. The war in Europe will be over in 2 months. The speed and scale of the Rhine crossings are only possible because of Bailey bridges. Traditional bridging methods would have taken far too long. Fixed bridges need solid foundations on both banks, which would require engineering work under fire that could take weeks. Pontoon bridges alone, without Bailey panels, would be too weak to carry heavy armor, and would be vulnerable to damage. But Bailey bridges supported by pontoons give the Allies exactly what they need. Strong, fast, reliable crossings that can be built and maintained under combat conditions. The longest Bailey bridge built during the war is at Nijmegen in the Netherlands. It's over 600 feet long, spanning the Vol River. It's built in less than 48 hours, and it stays in use for months, carrying everything from jeeps to the heaviest Churchill tanks. The Germans try repeatedly to destroy it with artillery and airstrikes, but it survives. Engineers keep repairing it, replacing damaged sections, reinforcing weak points. The bridge becomes a symbol of Allied engineering prowess and German frustration. After the war, when engineers analyze the logistics of the Allied advance across Europe, they conclude that Bailey bridges were one of the top 3 contributors to victory, along with landing craft and reliable logistics. Without Bailey bridges, the advance would have stalled at every blown bridge, giving the Germans time to regroup and establish new defensive lines. With Bailey bridges, the Allies could keep the pressure on constantly, never giving the enemy time to breathe. Let's talk numbers for a minute, because the scale of Bailey bridge production and deployment is staggering. Between 1941 and 1945, British factories produced over £200 million of Bailey Bridge components. That's enough to build over 100,000 individual panels. The US also started producing Bailey bridges under license in 1943, adding millions more pounds of components. By the end of the war, there are enough Bailey Bridge parts in Allied supply depots to build hundreds of miles of bridges. During the campaign in Northwest Europe, from D-Day in June 1944 to V-Day in May 1945, Allied engineers built over 3,000 Bailey bridges. That's more than 8 bridges per day, on average, for 11 months straight. Some are small, 30-foot spans over creeks. Some are massive, multi-hundred-foot structures over major rivers. Every single one is built faster than traditional methods would allow. The versatility of the system means it's used for things beyond just spanning rivers. Engineers use Bailey panels to reinforce damaged permanent bridges, allowing them to carry military traffic until proper repairs can be made. They used panels to build temporary piers and docks at captured ports. They used them to create elevated roadways over flooded areas or bomb craters. They even used them to build temporary housing, laying panels flat to create floors and walls. The system becomes a universal problem solver. And here's something that often gets overlooked. The Bailey Bridge saves lives, not just because it allows military operations to proceed, but because it's safer to build than traditional bridges. Combat engineers have one of the most dangerous jobs in the military. They work under fire, often at night, handling heavy equipment and explosives. Traditional bridging requires engineers to work in the water, on scaffolding, with cranes and winches, all of which are hazardous. Bailey bridges minimize that risk. Most of the assembly happens on solid ground, on the near shore. Engineers aren't hanging off scaffolding over a river. They're not diving in the water to position supports. They're on land, working with simple tools, doing work that doesn't require specialized training. The casualty rate among engineer units using Bailey bridges is significantly lower than units using older bridging methods. The German military watches the Bailey Bridge transform Allied logistics and tries to copy it, but they never succeed. German engineers attempt to build their own modular bridge system based on captured Bailey components, but they can't replicate the simplicity and standardization. German manufacturing is already overstretched, and they don't have the industrial capacity to produce Bailey-style components in sufficient quantities. More importantly, they don't have the logistics network to distribute the bridges where they're needed. By 1944, Allied air power has wrecked German supply lines, making it nearly impossible to move heavy equipment around. Even if Germany had Bailey bridges, they probably couldn't get them to the front lines. There's a story, possibly apocryphal but repeated by multiple sources, that Adolf Hitler is shown photographs of Bailey bridges being built across the Rhine. He looks at the photos, doesn't understand what he's seeing, and asks how long these bridges took to construct. When told a few hours, he thinks it's Allied propaganda and refuses to believe it. He's convinced that building a bridge capable of carrying tanks requires weeks of work with heavy equipment. The idea that you can do it in an afternoon with hand tools seems impossible. But it's true, and by the time Hitler realizes it, his armies are in full retreat, and there's nothing he can do to stop the Allied advance. After the war ends in May 1945, you might think that would be the end of the Bailey Bridge story. Military equipment becomes obsolete quickly. The tanks, planes, and guns of World War II are replaced by new designs within a decade. But Bailey bridges are different. They're so useful, so versatile, that they keep being used long after the war ends. In the immediate post-war period, Europe is devastated. Thousands of bridges have been destroyed, and reconstruction will take years. Bailey bridges provide temporary crossings that allow civilian traffic to resume, while permanent bridges are rebuilt. Some of these temporary Bailey bridges stay in place for years, even decades. In some cases, they're never replaced because they worked so well that there's no pressing need to build something else. Bailey bridges spread around the world. The British government essentially gives away the design to countries that need bridging solutions. Factories in dozens of countries start producing Bailey components, often with local modifications to suit regional conditions. Bailey bridges appear in India, crossing monsoon swollen rivers. They appear in Africa, spanning gorges in remote areas where building permanent bridges is economically impossible. They appear in South America, providing access to isolated communities. The military continues using Bailey bridges in every conflict after World War II: Korea, Vietnam, the Gulf War, Iraq, Afghanistan. Every time a military needs to move heavy equipment across an obstacle, Bailey bridges appear. The basic design hasn't changed significantly since 1941. Some versions use stronger steel or improved connectors, but the fundamental concept, panels pinned together, transoms and stringers, modular and scalable, remains the same. The civilian world adopts Bailey bridges too. Construction companies use them as temporary crossings during road. Mining companies use them to access remote sites. Disaster relief organizations keep Bailey bridges in storage for emergency deployment after earthquakes, floods, or other disasters that destroy infrastructure. Aid workers can fly Bailey proponents to a disaster zone, assemble a bridge in a few hours, and restore access to cut-off communities. One of the most famous post-war Bailey bridges is in New Zealand. In 1987, a permanent bridge collapses, cutting off a major highway. Engineers bring in Bailey components and build a temporary bridge, while a new permanent structure is designed and constructed. The temporary Bailey bridge stays in use for over 20 years, carrying thousands of vehicles per day, before finally being replaced in 2008. 20 years of continuous use for a bridge that was designed to be a short-term solution. That's how good the design is. Donald Bailey himself, the man who invented the bridge, doesn't become wealthy or famous from his creation. He receives a knighthood in 1946, becoming Sir Donald Bailey, in recognition of his contribution to the war effort. But the British government owns the patent on the bridge design, not Bailey personally. He doesn't receive royalties or licensing fees. After the war, he returns to civilian life, works as a consulting engineer, and eventually retires. He dies in 1985 at the age of 83. Respected but not celebrated, the way you might expect for someone who invented one of the most important pieces of military equipment of the 20th century. But his legacy lives on every time a Bailey bridge is erected. The principles he established, standardization, modularity, simplicity, manufacturability, those principles influence engineering across many fields. Modern modular building systems, prefabricated structures, even things like shipping containers, all owe something to the ideas Bailey pioneered. He proved that sometimes the best solution isn't the most complex or the most high. Sometimes it's the simplest idea, executed perfectly. Let's circle back to that fundamental question. How do you build a bridge that can span 400 feet and carry 30-ton tanks in just 3 hours? The answer isn't just about the Bailey Bridge itself. It's about the entire system that makes rapid bridging possible. The bridge is the star, but there's a whole cast of supporting elements that make it work. First, there's training. The British and American armies develop standardized training programs for bridge building. Every engineer unit goes through intensive training on Bailey Bridge assembly before deploying to combat zones. They practice in safe conditions until every soldier knows their role instinctively. They practice at night, simulating combat conditions. They practice with damaged or missing components, learning to adapt when things go wrong. By the time they reach the front lines, building a Bailey Bridge is almost automatic. The training includes something crucial: timing. Engineers don't just learn how to assemble the bridge, they learn to do it at speed. There are competitions between units to see who can build a bridge fastest. The record times are astonishing. Expert crews can build a 30-foot single bridge in under 30 minutes. A more complex 60-foot double single might take 2 hours. These times are achieved through practice, coordination, and understanding of the system. It's like a choreographed dance, every person knowing exactly where to be and what to do at each moment. Second, there's logistics. Building a bridge in 3 hours only works if the components are there when you need them. The Allied logistics system ensures that Bailey Bridge components are pre-positioned near likely crossing sites. Engineer units have their own dedicated transport, trucks loaded with panels, transoms, stringers, and all the other components, ready to move at a moment's notice. When an advancing unit reaches a blown bridge, they radio back for bridging equipment, and it arrives within hours. The standardization of components makes this logistics system possible. Every panel is identical. Every pin is identical. Parts made in a factory in Britain work with parts made in a factory in America. This means you can pool resources from different units if needed. If one unit doesn't have enough components for a long bridge, they can borrow from another unit, and everything will fit together perfectly. Third, there's reconnaissance and preparation. Engineers don't just show up at a river and start building. Before the bridge goes up, officers scout the site. They measure the span. They check the soil conditions on both banks to ensure it can support the bridge ends. They calculate what configuration they need based on the span and the expected load. They identify positions for equipment and staging areas. They plan the approach roads, making sure vehicles can reach the bridge from both directions. All of this happens before the first component is unloaded. In combat situations, this reconnaissance is dangerous. Engineer officers often go forward with the first assault troops, sometimes under fire, to identify crossing sites and assess conditions. They're looking for places where the banks are accessible, where the current isn't too strong, where the enemy has the weakest defenses. A good crossing site can make the difference between success and disaster. Fourth, there's combined arms support. Building a bridge in combat isn't just an engineering task. It's a military operation that requires coordination with infantry, armor, and artillery. Infantry secures the bridgehead, clearing enemy troops from the near bank and suppressing fire from the far bank. Artillery provides covering fire, hitting enemy positions that could threaten the bridge builders. Smoke shells create a screen that obscures the bridge site, making it harder for enemy artillery to target the engineers. Sometimes aircraft provide air cover, shooting down enemy planes that try to bomb the bridge. This coordination is critical. Engineers are vulnerable while they work. They're exposed, often in the open, focused on assembly rather than defending themselves. They rely on other units to protect them. When that protection works, bridges go up fast. When it fails, the results are tragic. There are instances during the war where bridges are destroyed multiple times by enemy fire before finally being completed. Engineers keep trying, replacing casualties, starting over, refusing to give up. Fifth, there's adaptation and innovation. The basic Bailey design is brilliant, but engineers in the field constantly find ways to improve it or adapt it to specific situations. They develop techniques for building in fast currents, using extra anchors, or positioning pontoons at angles to the flow. They figure out how to build on unstable banks, using timber cribbing or rock fill to create solid foundations. They improvise repairs, using whatever materials are available when proper replacement parts aren't at hand. One innovation that becomes standard practice is the use of Bailey bridges as approaches to permanent bridges that have been partially destroyed. Often, the center span of a permanent bridge is blown while the approaches on either side are intact. Engineers build Bailey bridges from each bank to the remaining sections of the permanent bridge, creating a hybrid crossing that uses less Bailey components than spanning the entire gap would require. Another adaptation is the use of Bailey panels for temporary repairs to damaged permanent bridges. If a bridge has a weakened section but is still partially intact, engineers can bolt Bailey panels alongside or underneath the damaged area, reinforcing it enough to carry traffic until proper repairs can be made. This technique saves countless hours and allows the use of existing infrastructure rather than building entirely new crossings. The Bailey Bridge also proves invaluable in terrain that isn't just about crossing water. In mountainous regions, deep gorges and ravines are just as much obstacles as rivers. Bailey bridges span these gaps, allowing roads to pass through terrain that would otherwise be impassable. In the Italian campaign, where the terrain is notoriously difficult, Bailey bridges are used extensively to keep supply lines open through the mountains. One of the most impressive uses of Bailey bridges in difficult terrain is in Burma, during the campaign against the Japanese. The Burma Road, the supply line to China, crosses some of the most challenging terrain on Earth. Deep jungle, seasonal monsoons that wash out roads, rivers that can rise 20 feet overnight. Bailey bridges become essential. Engineers build and rebuild bridges constantly, fighting not just the enemy but the environment. Some bridges are destroyed by monsoon floods and rebuilt multiple times. The engineers become expert at rapid construction because they have to. There's no other choice. The Japanese military, facing these same terrain challenges, never develops an equivalent to the Bailey Bridge. They rely on traditional bridging methods, which are slower and require more resources. This gives the Allies a significant mobility advantage. Areas that the Japanese think are impassable become Allied supply routes. Offensives that should be impossible because of destroyed infrastructure happen anyway because Bailey bridges restore mobility within hours. After the war, when military historians analyze the Burma campaign, they identify logistics and bridging as key factors in Allied victory. The Japanese had brave troops and skilled commanders, but they couldn't match Allied logistics. Bailey bridges are a big part of that advantage. Let's talk about cost for a moment, because one of the remarkable things about the Bailey Bridge is how economical it is. A Bailey Bridge costs a fraction of what a permanent bridge costs. The components are made from standard steel, using conventional manufacturing techniques. No exotic materials, no specialized processes, just good engineering. A typical 60-foot Bailey Bridge, complete with all components, costs about the same as a single Sherman tank. But while a tank might get destroyed in its first battle, a Bailey Bridge can be used, disassembled, moved, and used again dozens of times. The return on investment is incredible. One set of Bailey components might support a dozen different crossings over the course of the war. After the war, those same components might be used for another 50 years in civilian applications. The cost per use is almost negligible. This economic efficiency is part of why Bailey bridges spread so widely. Even poor countries can afford them. The environmental impact is also worth mentioning. Traditional bridge building often requires excavating foundations, pouring concrete, disturbing the riverbed, all of which have environmental costs. Bailey bridges have a much lighter footprint. The supports rest on the surface or on simple pilings. When a Bailey bridge is no longer needed, it can be completely removed, leaving almost no trace. In modern times, this makes Bailey bridges attractive for temporary crossings in environmentally sensitive areas. There's also a human element to the Bailey Bridge story that often gets overlooked. The men who build these bridges are combat engineers, soldiers who face the same dangers as infantry but don't get the same recognition. Building a bridge under fire requires not just technical skill, but courage. Engineers work knowing that there are exposed targets, that enemy artillery or aircraft can hit them at any moment. They work through exhaustion, often at night, in all weather conditions. Many of them were killed or wounded while building bridges. They deserve more credit than they typically receive. After the war, many of these engineers return to civilian life and use their skills in construction, manufacturing, and other fields. They're part of the generation that rebuilds post-war Europe and America. The discipline and problem-solving skills they learned building Bailey bridges under fire serve them well in civilian careers. In a very real sense, the Bailey Bridge doesn't just help win the war. It helps win the peace by training a generation of skilled workers and engineers. The Bailey Bridge also influences military thinking about logistics and mobility. Before World War II, armies accepted that rivers and destroyed infrastructure would slow advances. Planners built long pauses into their schedules to allow time for bridging operations. After the Bailey Bridge proves its worth, that thinking changes. Military planners realize that with the right equipment and training, mobility can be maintained almost regardless of terrain. This changes how wars are fought, emphasizing rapid movement and exploitation of breakthroughs. Modern military bridging systems owe a direct debt to Donald Bailey. The British military develops the medium girder bridge in the 1970s, which uses many of the same principles as the Bailey, but with improved materials and connectors. The American military develops the ribbon bridge, a floating bridge system that combines pontoons with modular deck sections. The German Bundeswehr uses the Biber bridge layer, a tank-based system that can deploy a bridge in minutes. All of these systems, and many others around the world, incorporate lessons learned from the Bailey Bridge: standardization, modularity, simplicity, speed. The Bailey Bridge even influences civilian infrastructure thinking. The idea that you can solve complex problems with simple, modular solutions becomes influential in many fields. Prefabricated housing, modular construction, even modern manufacturing techniques like just-in-time production, all reflect some of the principles that made the Bailey Bridge successful. There's a philosophical dimension to the Bailey Bridge story that's worth considering. Donald Bailey's insight was that complexity isn't always the answer. Military engineers in the 1930s were trying to build better bridges by making them more sophisticated, with clever mechanisms and advanced materials. Bailey went the opposite direction. He made his bridge simpler, not more complex. He eliminated everything that wasn't absolutely necessary. He focused on the fundamental requirements and designed the simplest solution that met them. This approach, radical simplicity in the service of effectiveness, runs counter to much of engineering culture, which often celebrates complexity and technical sophistication. But Bailey proved that sometimes the elegant solution is the simple one. His bridge isn't impressive because it's complicated. It's impressive because it's not. This lesson has broader applications. In many fields, we tend to add complexity to solve problems, assuming that more sophisticated solutions are better. But often, the most effective solution is the one that strips away everything unnecessary and focuses on the core requirements. Bailey's Bridge is a reminder that genius sometimes lies not in adding, but in subtracting, in finding what you can eliminate while still meeting your goals. As we reach the end of this story, let's return to where we started. March 1945. The Rhine River, engineers building a bridge in 3 hours. That scene represents more than just military engineering. It represents human ingenuity, the ability to solve seemingly impossible problems through clear thinking and practical design. It represents courage, soldiers working under fire to complete a mission. It represents the industrial power of democracies that can produce endless quantities of equipment and distribute it efficiently. and it represents the principle that sometimes the simplest solution is the best solution. The Bailey Bridge helped win World War II. That's not hyperbole or exaggeration. Without it, the Allied advance across Europe would have been far slower, giving Germany time to regroup and fortify. The war would have lasted longer, cost more lives, and might have ended differently. D-Day succeeds partly because Bailey bridges restore mobility after the initial landings. The Rhine crossing happens in days instead of months because of Bailey bridges. The final push into Germany is possible because Bailey bridges keep the supply lines open. Donald Bailey never sought fame or fortune. He was a civil servant who saw a problem and solved it because that was his job. His reward was a knighthood and the satisfaction of knowing that his invention saved lives and helped end a terrible war. That's enough for most engineers. The knowledge that their work mattered. Today, more than 80 years after Donald Bailey sketched his design on the back of an envelope, Bailey bridges are still in use around the world. They span rivers in dozens of countries. They provide access to remote communities. They appear in disaster zones when hurricanes or earthquakes destroy infrastructure. They support construction projects. They serve as temporary crossings while permanent bridges are built or repaired. Every time a Bailey bridge goes up, whether in a war zone or a natural disaster area or a civilian construction project, it's a testament to simple, brilliant engineering. 400 feet across a river in 3 hours. 30 tons of tank rolling across water that was a barrier just hours before. It's still remarkable, even after all these years. Want to see how the rest of Allied logistics won World War II? Subscribe for more.